Okay, this is part three, is device engineering. Probably the most important or the most interesting portion of this presentation. And you know why I always put this that there. Um, Engineering design principles. So the reason why we need to do engineering design, because we do not want to be spending our lives repeating experiments, not understanding what's going on, like I did 20 years ago. Okay, so you have seen this. Basically, there are four engineering design principles. First is spatial velocity gradient. Second is asymmetric and non-canceling fields. Third is vectoring. And fourth is modulation. When we design an engine, we have to have a gravity modifying engine. We have to have take into account these four considerations. Okay, spatial gradient. As I said earlier, we are looking at the direction of the increasing velocities that gives us the acceleration. But what can lead us astray is that changing the direction of the E field or the B field to reverse the electromagnetic velocity, like in here, I've changed the E field, direction of the E field, does not necessarily change the gradient. So when you're designing your device, you have to be aware that what you are interested in is designing the gradient, not the velocity vectors. Okay. And the second piece is that there must be, if you recall the electron motion, the electron is moving with its electric field sticking out like that, and it's moving in a magnetic field and cutting the magnetic field. So the same thing with this, we have electric field that cuts the magnetic field as it moves. So that's a second important consideration. There must be a relative motion between the magnetic field and the magnetic field, so that to get the maximum effect, the electromagnetic velocity must be parallel or anti-parallel to the rotational tangential velocity. That's where you maximize it. Okay, so when we are designing, we want this gradient. If we don't get that gradient, you won't see a force. If you mess up your magnetic field design, you won't see that force. You won't see that acceleration. Okay, so with particle knobs, what we now see is a bilayer disk with the lower magnetic field trapped in, because he charged the upper semiconducting disk with electric field. And so we have a magnetic field that is exposed to the electric field. And that's a diagrammatic version. You can put two electrodes, two plate-like electrodes, because we now don't need a superconducting disk. You can put two plate-like electrodes where it overlaps the upper magnetic field. And when you rotate, when you spin the magnetic, the disk, you get the electromagnetic velocity, and you have to watch for this gradient that's being created in the combination of the rotational mechanical velocity and the electromagnetic velocity. Okay, so that's the equation. It's the mechanical velocity is equal to the rotational plus or minus electromagnetic velocity. So as I had said earlier, even if you reverse E and B, it will not necessarily change the gradient. So you have to take care of that. And this is the formula for the electromagnetic velocity, where m is the mass, and you have B, E, and D. B is the magnetic field, E is electric field, and D is the height from above the surface of this disk. But take care, because when you do the calculations, sometimes the B and the D will cancel out, and you won't get that orthogonal naive field effect. And modeling results. Okay, this is in December 2019, I formed a meetup group called the Gravity Modification Today. Today is in response to Michio Kaku having said that gravity modification is something we'll only be able to do in about 300 or 400 years. Nonsense. So this is the approximate dimensions we had come out of the discussion. The two key people who were involved in the discussion was Mike Doty, who you could say is the principal designer, and John Sokol, who you could say is the principal engineer behind this reconstruction. And so we could replace this with a bar or disc magnets instead of having a superconducting field. And we looked at Chokokov's experiments, and he was using disc magnets. But the group as a whole didn't feel comfortable with Chokokov's experiments, even though we tried to dig into it. We even actually invited him to come to talk to us over Zoom, and he gave some excuse about the Russian government and said, okay, that's it, enough, fine. So when you look at the bar magnets, I believe these are the correct serial numbers for this bar magnets and the disc magnet. The bar magnet has a field strength of 1.42, and and the disc magnet is a bit stronger, but for modeling purpose, I set it at 1.42 because I wanted to compare one for one, apples for apples, oranges for oranges. The key thing about the disc magnet versus the bar magnet is that this field dissipates as a function of the distance, r squared, the square of the distance. Whereas for a disc magnet, the field dissipates as a function of r cubed, 1 over r cubed. So this gradient of this magnetic field at the of a disc magnet, or the edge, if essentially it's the edge of this magnet, it's equivalent to that. It's a much stronger gradient than this the bar magnet. And so when I built a crude model. By crude model, I mean you have a bar magnet, you draw a line above the bar magnet, and then you find the change in the field about that line, very small distance. And then you don't build a model of the whole area of the bar magnet. You just build a model of a line across that magnet, because we want some quick results. We want to be able to show what is a good design, what is a reasonable design that'll give us answers, instead of saying, should it be 1 centimeter? Should it be 10 centimeters? Should it be 50 centimeters? No, this gives us a good estimate of what the size and the shape of the device should be. And what we see, to my surprise, when I showed this at the meetup group, I had just slapped on the two graphs on each other, and I had not noticed this effect because when you're busy trying to do things quickly. For this presentation, I put them all on the same graph, and something comes up very clearly noticeable, that for this magnet gives a much higher effect than a bar magnet, and it's due to this r squared versus r cubed. The other thing we noticed is that for a bar magnet, the peak is about I think 1,002, 1,200 RPMs, and for a disc magnet, the peak is greater, but it's at 1,100 RPMs. So beyond that, there's no effect. So if you're running at 3,000 RPMs for the fields we have shown and for the physical size of the device, you're not going to see anything. and you think that now result, the device doesn't work. There's no such thing as gravity modification or anti-gravity or whatever you want to call it. Second result is that I changed the disk size, 15 centimeters in diameter, 12, 6, 3. And you can see that the peak, as you change the disk size, the peak requires more RPMs and to reach the peak before it dissipates. And the other thing you notice is there's some disturbance in here that becomes more and more pronounced. That means as you go further out, as you reach higher RPMs, you need higher RPMs for a smaller disk. You get this coming in as noise and making it difficult for you to see what's going on. I heard an interview of Portlanov a few years back. I think it was on American Anti-Gravity, because when I was Googling for this sort of things to present here, I wanted to find out what other things were out there. And it shows that if you extrapolate these peaks out here, it shows that for Portlanov to be operating at 13,000 RPM or 18,000 RPM, he's using a disk size of about 1 centimeter, which makes sense since he's using atomic gold layers, which is expensive. So you cannot have a big disk. So that makes sense. The surprise, it's a pleasant surprise. I plugged in various voltages, 10,000, 60,000, I think it's 125,000, 253,000 volts. I cannot read that. And I found that voltage is immaterial. You need voltage to create the electromagnetic velocity, but it is not important to the effect. Other than that, it's not important to the effect because all four graphs lie on the same line, which means that we can run this experiment at 500 volts. You don't need a 200,000 volt generator. You can run it at 500 volts, which is good news. Until the experiment tells you it's wrong. So the close to the final design, I realized I had not answered one question. Where was the power coming from? And that set me into a panic. And then I went back and looked at all the data and I realized, okay, it's not from the electric field because the effect is not dependent on the electric field strength. It's not from the magnetic field because the magnetic field is not mutable. It's fixed. It's from a regular magnet. It's not from an electromagnet. And if it was the magnetic field should deplete. We don't know, but I believe that the magnetic field does not deplete. And so it's not from the magnetic field. The only conclusion was that the power was coming from the rotation of this disk. So, so that was how the rotation, the energy of the rotation was being transferred to the field effect to get the Bill and I fields to see the acceleration. Power of falsifiability. And this is the reason why falsifiability is important. If you look at the SEC, SEG, you find that the electric field and the magnetic field and the pointing vectors are in that orientation. At the back and at the front, it's in this orientation. So we can ask a few questions. Could it be that the electric field here, since it is rotating, the rollers are rotating, the electric fields are crossing the magnetic field lines here. The electric field here, it comes around and crosses the magnetic field line here, there. So could it be that the nigh field is creating the force effect? I don't know, but it's something to think about because recall the electron motion. The electron motion is basically the electric field crossing the magnetic field, that forming a gradient that causes the force effect. And then this simple diagram took me about 2 days to get it right, and I still think it's not correct. The first puzzle is the rollers. When the whole thing spins, the rollers come off the plate. That cylinder is called a plate. They come off the plate and they are slightly above it. So where's the repulsion coming from? Is it centripetal? Is it magnetic? That's an interesting question to answer. And I tell you, I wouldn't have been able to answer this question if Paul Murad and John Brandenburg hadn't done such a good job of documenting what they had seen. When the poles are the same, when they are reversed, this is the magnetic field circuit. When they are not reversed, then you have opposite circuits, magnetic circuits. One is going this way, and on this side, the roller side, is going the opposite direction. So the question is, what's causing this repulsive force? Obviously, that the magnetic field is holding it together, working against the repulsive force. But it's interesting and important to find out what's going on. It helps us investigate what else is going on and why is it going on. And this diagram, it's not quite right, but I left it wrong because I hope somebody will point out to me that, hey, this diagram is wrong. But if you look at this area, at the top of the poles, there's a magnetic field bleed where the north cuts across to the south plate. And so you have some leakage where the strength of this field is much greater than if the magnetic field went round it. So the question is, of course, since E and B are essentially in the same direction, there's no pointing vector in this area, in this region. At least that's what I think. So the question is this changes in field strength, is that what causes more rollers to become more effective as a force generator than less rollers? And of course, I'm not the person who can answer that question. It's an interesting question to ask because it tells us, it informs us more about what's going on. And we understood the purpose of engineering design principles, how it can substantially speed up what we're doing, and how falsifiability enhances the debate. Okay, end of story. That's where I am here, a SaaS credit risk business. And we are open to questions. I hope we have enough time, or we can ask at a later session.
No, actually, that's wonderful. Let's do a very quick session. But before we do that, let me put it on gallery view and let me see. I'm going to, I'll stop your sharing, put it on gallery view. And everyone, I would like you to give a giant hand for Benjamin T. Solomon. Thank you,
Hey,
sir.
thanks, folks.